Let's consider the properties of this simplest Carnot cycle of ideal gas. In an isothermal process, the heat is determined by the initial and final volumes. Then, we check the value of Q1 over T1 plus Q2 over T2. Replace the heats by the volumes. Introduce gamma minus 1 to the denominator and the power of the logarithm. Multiply the denominator and numerator of the logarithm by P1 V1 P2 V2 P3 V3 P4 V4. We know that, in an adiabatic process, PV to the power of gamma is a constant. From state 2 to state 3 is an adiabatic process, so the related terms cancel each other. Similarly, the terms related to state 4 and state 1 cancel each other. Replace PV by nRT according to the idea gas law. We find that the term in the logarithm is 1, so Q1 over T1 plus Q2 over T2 is 0. This result can be generalized to any reversible cycle because the cycle can be divided into infinitesimal isothermal and adiabatic steps. Delta Q is the infinitesimal heat in an infinitesimal isothermal step. Suppose there is a certain initial state and a certain final state. R and R' are two arbitrary reversible processes connecting them. The integral of delta Q over T along R and inverse of R' forms a reversible cycle. That means that the integrals of delta Q over T along processes R and R' are equal. Thus, the integral of delta Q over T only depends on the initial and final states. It is independent of the path. It is the change of a state function. We define this state function entropy. The infinitesimal change of entropy is delta Q over T. Accordingly, delta Q equals TdS. Thus, the first law of thermodynamics can be expressed in the following form. Similarly, the infinitesimal change of enthalpy can be expressed in the following form. Now, the Carnot cycle can be visualized with an entropy versus temperature plot. The isothermal processes are the horizontal lines. The adiabatic processes are the vertical lines. Such both adiabatic and reversible processes are also called isentropic processes. Some work is done by the so-called Carnot engine to the surroundings in a cycle. Since the internal energy change is zero, the opposite of work is heat. In an isothermal process, the heat is T times delta S. It is the area below the function. So, Q1 plus Q2 is the difference in the areas of the rectangles. Pay attention to the sign of the heat. It depends on the direction of the process. The work is the area inside the Carnot cycle. The efficiency of a heat engine is defined to be the ratio between the work done to the surroundings and the heat received by the engine. The efficiency of Carnot engine has such expression. Let's check the entropy change in heat conduction. Suppose the temperatures of the warmer and colder water are T1 and T2, respectively. The heat passes from hot water to cold water. It is indeed Clausius' statement of second law of thermodynamics. It states that heat can never pass from a colder body to a warmer body without some other change. Here, the other change is work. Suppose the heat of the warmer water is minus delta Q. Then, the heat of the colder water is delta Q. We can find that the entropy change of the whole isolated system must be positive. It leads to the Planck statement of second law of thermodynamics. It states that the entropy of an isolated system always increases. So, entropy is called the arrow of time. In an isolated system, the direction of process depends on its entropy change. If a process increases the entropy of an isolated system, it happens spontaneously and irreversibly. If in a process, the entropy of an isolated system is a constant, the process is reversible. Let's have a look at our previous example of free expansion. Since entropy is a state function, its change can be calculated using any pathway with the same initial and final states. And because the temperature does not change during the free expansion, it is convenient to calculate the entropy change using an isothermal process. We can find that, in a free expansion, the final volume must be greater than the initial volume. So, the entropy increases in free expansion. That is in accordance with the Planck statement of second law of thermodynamics. There are various equivalent statements of second law of thermodynamics. Though, I will not prove the equivalency between them. Here, I show you two of them. Kelvin's statement of second law of thermodynamics states that no process is possible whose sole result is the complete conversion of heat into work. The perpetual motion machine of the second kind, which spontaneously converts thermal energy into mechanical work, violates the second law of thermodynamics. So, it is impossible. The Carnot statement of second law of thermodynamics states that a Carnot engine is the most efficient possible heat engine using two temperatures. Here, I have an example of a Stirling engine based on two isothermal and two isochoric processes. The efficiency is the ratio between the opposite of work and the heat received, where the opposite of work is the total heat. The heat of an isothermal process is calculated with the initial and final volumes. The heat of an isobaric process is calculated with the initial and final temperatures. If we assume that the heat capacity at constant volume is independent of temperature, the heats of the two isochoric processes cancel each other. We can express the heat capacity at constant volume with the adiabatic index. Then, the efficiency of the Stirling engine is expressed as follows. Pay attention, the term in the denominator is positive. So, we proved that the efficiency of Stirling engine is lower than the Carnot engine using identical hot and cold reservoirs.